Hello, everyone. My name is Lana. I'm a grad student at the Perimeter Institute, and today I'll be sharing a work that was done in collaboration with Alex May and Stanley Miao on entanglement summoning from entanglement sharing schemes. Okay, so let's get into the background. So the main motivation for our line of work is that we want to understand quantum information with relativistic constraints. So what I mean by this is that we have this very basic question of what is physically possible when we impose certain quantum mechanical and relativistic constraints. So for example, from quantum mechanics, we have some basic physical principles such as the no cloning theorem, the monogamy of entanglement, etc. And from the relativity side, we have no signaling. So we can't send information faster than the speed of light. So we want to understand how information theory works in this framework. And so the first sort of bare bones no-go theorem that was written down in this space was discovered by Adrian Kent in 2011, and it's called the no summoning theorem. And the setup goes like this. Can people see my cursor? Okay, great. Yeah, so we have some uh, quantum state that's initially localized at some spacetime point S. And then a request will be made at one of the call points that are in the causal future of S, and then according to which point gets the call, we need to send it to the appropriate reveal point. So for example, if I get a call at C1, we need to forward the quantum state to R1, and similarly for C0, we need to forward it to R0. Now, the no summoning theorem states that this task cannot be completed successfully 100% of the time if the call points are space-like separated. And we can see this very intuitively from the perspective of QI and SR. So since we have a quantum state, we can't just clone the state and send one copy to R1 and one copy to R0 to complete the task every time. So we have to make a choice on whether or not we'll send the state to C1 or to C0. But say we send it to C1. If C1 gets the call, that's great. We can just forward it to R1 and the task is done. But if C1 wasn't the correct call, we know that the state must go to R0. But since C1 and R0 are space-like separated, and we can't send information faster than the speed of light, we will fail at the task. So in this specific setup, we'll get a 50% chance of completing the task successfully with this protocol. So the next natural question to ask after understanding when summoning isn't possible is, well, when is it possible? And this was characterized by Patrick Hayden and Alex May, and they established a theorem that characterizes all possible instances of single-state summoning. And to do this, they first define a notion of a causal diamond. So a causal diamond is assigned to every single call and reveal pair in the setup. And this is just going to be the space-time region that is the intersection of the causal future of the call point, Ci, and the causal past of the reveal point, Ri. Then they state this single-state summoning theorem as the following. Summoning is possible if and only if, first of all, every reveal point is in the causal future of S, which makes sense because to complete the task, the initial state needs to be able to go to every reveal point. But more interestingly, we also require that for every single pair of causal diamonds, there is a causal connection between them. So for example, in this setup, we see that, well, first of all, R0 and R1 are in the causal future of S. But more importantly, we see that there is a causal curve from D0 to D1, which means that the task is possible. And now one thing that we can immediately see is that the completion of this task doesn't rely at all on the exact space-time position of the call and reveal pairs. All we care about is the connections between any two causal diamonds. So really, we can reduce the geometry of our summoning task to a graph problem. So here, for example, we have another task with a bunch of call and reveal pairs, but we can reformulate the task of summoning in terms of this causal graph, where the vertices will represent the causal diamonds for every single call and reveal pair, And then the edges will be the causal connections between the diamonds. And as we saw, we only care about these. We don't care about the specific space-time positions. We can restate the summoning theorem as the following. Summoning is possible if and only if the causal graph is a tournament. And a tournament is just a graph that is all-to-all connected. So we saw that every single causal diamond needs to have some connection between them. And this is exactly the tournament condition that we see on this causal graph. Now, after understanding this single state summoning task, the sort of natural follow-up to this is, what about bipartite state summoning? In particular, there are many quantum network scenarios or cryptographic scenarios where you want to, you have a bunch of parties and you need a bell pair to be summoned between two different parties. And that leads us to the task of entanglement summoning, which generalizes single state summoning to the case where we want to summon a bell pair. And so the formal definition of this task goes like this. An entanglement summoning task is specified, again, by a set of causal diamonds, each of which is defined by a call and reveal point. And we have two agencies involved in this task, Alice and Bob, and they perform the following. At every single call point, CJ, Bob will give Alice some classical bit, BJ. And Alice has promised that exactly 2 of these bits, BJ star and BK star, will be equal to 1 for some choice of J star and K star, but these are unknown to her beforehand. So she knows that 2 of her causal diamonds will receive calls, but she doesn't know which diamonds they will be. And then we'll say that this task of entanglement summoning is achievable if for any choice of J star and K star by Bob, Alice can return a system A at RJ star and B at RK star, such that the total state on AB is the maximally entangled state. So this is exactly like the single state summoning scenario, except now we need to summon one half of a bell pair to one diamond and another half of a bell pair to the other diamond. Now, previously, entanglement summoning was only characterized in the case of oriented causal graphs. So in the case where the causal graph only has directed edges between any 2 diamonds, Delev, May, and Wan came up with this theorem characterizing when those summoning tasks are possible. And the theorem states that an entanglement summoning task whose causal graph is an oriented graph is possible if and only if the subgraph induced by this set Sj is a tournament. And these set Sjs are just going to be defined for every diamond DJ as all the diamonds that don't point into it. So here's an example of an entanglement summoning task that is oriented, that is possible. So we see that this set S1 is defined as all the diamonds that don't point into D1, which will be D3 and D2. Similarly, S3 will be all the diamonds that don't point into D3. And for D2, S will just be empty. And we see the subgraphs induced by S1 and S3 are tournaments. So this entanglement summoning task is possible. So it is achievable. So in our work, we wanted to close some of the gaps in the literature, including characterizing the bidirected entanglement summoning case. So as opposed to having only oriented edges between every single causal diamond, now we'll have only bidirected edges between all the diamonds. And then we partially characterize the most general case where we can have both oriented and bidirected edges, and we provide sufficient conditions on causal graphs being achievable. And the way we go about doing this is we leverage something called entanglement sharing schemes. So entanglement sharing schemes are very related to the task of summoning, but in this case, instead of being a space-time problem with some timing constraints, we will just have some quantum state along with an access pair structure. And so what I mean by this is we have some dealer that prepares a state that is split up between n different parties, and every party gets a share of this state. And on this state, we'll define an access pair structure that is composed of the authorized sets and the unauthorized sets. So every single element in the unauthorized or authorized sets is going to be some pair Ti and Tj, where these Ti T's are going to be groups of the subsystems of our original state. And what we want is that every single authorized pair should be able to, by some local maps on their respective subsystems, be able to recover a maximally entangled state. And similarly, any unauthorized pair should never be able to recover a state arbitrarily close to the maximally entangled state. And what we call the entanglement sharing scheme is this quantum state along with this access pair structure. So just to illustrate an example of this scheme, let's consider a state that is split up between 5 different parties. And say I want to group S1 and S2 together to form one T, and then S3 and S4 together to form another T, call that T3. And I want these to form an authorized pair so that when the T1 acts locally on S1 and S2, and a T3 acts locally on S3 and S4, they can recover a Bell state. So I will call T1 and T3 an authorized pair. Then I can go around and group any subsystems I want together, and I want to dictate that when there is a green line, those connecting two groupings of subsystems, that I want them to be able to recover a Bell pair. So this is sort of an illustration of how this access pair structure works. Now, the neat thing about sharing schemes or entanglement sharing schemes is that they can also be described with a graph. In this case, we have an undirected graph known as the access pair graph. And the vertices are going to be these groupings of the subsystems of our original states, and the edges will represent authorizations between the pairs. So this star is the access pair graph representing this scenario where I grouped S1 and S2, so on and so forth together, and drew this star shape to represent the authorizations. Now, there's a special case of entanglement sharing schemes that will be relevant for the problem of entanglement summoning, and that is the case where we have no unauthorized sets. So we only have authorizations between pairs, but we don't necessarily want to forbid any given pair from recovering a Bell state. And so this work from some folks at the Perimeter Institute characterized a bunch of these entanglement sharing schemes. And specifically, in the case for no unauthorized sets, they have this theorem stating when an access pair structure is realizable as an entanglement sharing scheme. And this can happen if and only if the following condition is satisfied, and this condition is known as monogamy. So it tells us that for any even length path in the access pair graph of S, it is the case that the start and end points must have non-zero overlap. So they have to have some subsystem in common. So if we just define some random access pair structure, as long as it satisfies this monogamy condition, that access pair structure can be realized as an entanglement sharing scheme. So now the main idea of how we'll use this is what we find is that we can map the problem of summoning to entanglement sharing, and then we can just use this entanglement sharing characterization theorem to tell us which summoning tasks are indeed possible.
Sorry, can I quickly ask a question?
Yeah.
So in this previous theorem that you mentioned on the previous slide, so here they give an explicit construction, is it? When this condition is satisfied, they give an explicit scheme for entanglement sharing?
That's a great question. I feel like Alex, maybe you're better equipped to.
Yeah, we do.
Okay.
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 Yeah, I think there's even like a stabilizer code kind of construction. It's not too hard.
Okay, thanks.
Thanks for that, Alex. Yeah, so yeah, as I mentioned, what we'll do is we'll map summoning to sharing and then use that monogamy theorem to characterize when summoning is possible. And that leads us to the results of our paper. So first, we handle the bidirected case, which is a lot nicer. And just to remind you, this bidirected summoning problem is where the causal connection between any two given diamonds is going to be a two-way causal connection, so that yeah, they can talk to each other. And the nice thing about this case is that we can restrict our attention to the case where non-neighboring diamonds receive calls. And the reason we can do this is because, say, for example, in this setup, D1 and D2 receive calls. Well, they can see that their nearest neighbor got a call, so we can handle that case with a dedicated EPR pair. If you just see that your neighbor got a call, we pre-share some EPR pair in the resource state that we send out to every single diamond before completing the task, and the task can be trivially completed. So the only case that we really need to consider is when non-neighboring diamonds receive calls, because they have no communication between each other. And the procedure that we'll do to map this problem of summoning to sharing is as follows. So first, we'll prepare some resource state that is split up into n different subsystems based on how many diamonds are in the causal graph, and we'll send xi to the diamond di. Then Alice will apply a map at every single diamond that maps that share that diamond received into a bunch of different shares based on how many outgoing edges that diamond has. So for example, at D1, we'll map X1 to a share that can go to D2 and a share that can go to D5. Then, if that diamond does not receive a call, it will just forward all the shares out, or the appropriate share to the diamond. So for example, if D1 does not receive a call, it will forward the share prepared for D2 to D2, and similarly for D5. But if that diamond does receive a call, it will just wait to receive some information from its neighbors, and then forward all the outputs that it receives to its reveal point. So let's illustrate this with an example in this pentagon case. So first, as I mentioned, we'll prepare some resource state and then send out every xi to di. Then we'll apply our map that splits up that share into multiple different subsystems based on the outgoing edges from that diamond. Now, suppose that diamonds 1 and 3 get calls. We know that in this case, those diamonds will keep all of their shares, and every single other diamond will forward their shares. So from D2, for example, we'll send Y2 to 1 along this channel and Y2 to 3 along this channel, and similar for every other diamond that didn't receive a call. Now, at the end of the day,
can I?
Oh yeah.
Can I get a small clarification? So okay, the model is very new to me, so this may be completely stupid, but so the call you're supposed to receive at a certain time simultaneously. Is that the setup? Like are all the nodes, or do they like get a message that you have been called and you haven't been called? Like one of those. I'm just trying to imagine how the. So go ahead.
Yeah, you can just imagine that all the calls happen simultaneously. So at some point, like every diamond is given like a bit, and if that bit is 1, you've received a call. If not, then you know that you haven't received the call. And and every other diamond also knows that only 2 of the diamonds in the causal graph will receive the call as well.
The promise.
Yeah.
Got it. Thank
you. Yeah, no worries. Yeah, so at the end of the day, in this example, all the shares that end up at D1 will look like this, and the shares that end up at D3 will look like this. But now we remember that in this summoning task, at the end of the day, everything at D1 should be able to recover half of a bell pair, whose other half should be recoverable from the subsystems at D3. So in the entanglement sharing scheme language, we see that we can define all the subsystems that go to D1 as this T1 grouping, and then at T3, this grouping of subsystems as all the information that goes to D3 when it receives a call, and they form an authorized pair because we need to be able to recover a bell pair from the information that ends up at both of these diamonds after the procedure that we implemented. So we now have an authorized pair. And we can go on and do this for every single pair of calls between non-neighboring diamonds. And the way that every single TI is defined, it will just be all the subsystems that go to that diamond when it receives a call. And it will basically just get all the information from its nearest neighbors. But now we see that since we're only handling the case where non-neighboring diamonds receive calls, the access pair graph is just going to be the complement to the causal graph, because we saw that we want diamond 1 and diamond 3 to be able to summon, diamond 3 with diamond 5 to be able to summon, etc. So the access pair graph is just going to be the undirected complement of the original causal graph. And so this access pair structure, along with the state that's defined on all of these Y shares that we split into, is going to define an entanglement sharing scheme. And now, if we recall, all we need to do to see if this is a valid entanglement sharing scheme, if it's achievable, we just need to make sure that this access pair graph satisfies monogamy. And then that will tell us if the original summoning task is achievable. And what we show in our work is that for an entanglement sharing scheme that is derived from a summoning task, so just this procedure that we went through, this monogamy condition is equivalent to saying that there are no odd cycles in the access pair graph of S. So really all we have to check for is whether or not the complement of the causal graph has an odd cycle. And if it doesn't, then it's achievable, but if it does, it is not achievable. And so combining all our previous analysis, that leads us to one of our main theorems, characterizing bidirected entanglement summoning and when it is achievable. And we have an if and only if condition stating that it's achievable when the complement of the causal graph contains no odd cycles. So this is really nice. We get a very simple theorem that tells us when bidirected entanglement summoning tasks are achievable. All we have to do is look at the complement graph, and for example, in these two, they're not achievable because they have they both have a 3 cycle in their complement, but these, for example, are achievable because they don't even have any cycles in their complement graph. So this sort of closed the open problem of bidirected entanglement summoning tasks in a very simple manner, which was really nice. But a really neat thing is that we can make use of some graph theory to get an even more natural characterization of our theorem in terms of the original graph instead of talking about the complement. And to do this, we'll first introduce this notion of co-bipartiteness. And a graph whose complement has no odd cycles is co-bipartite. So that means that the entanglement summoning tasks that are possible must be co-bipartite, since their complement, as we saw, must have no odd cycles. Now, there's this theorem that states a graph G is co-bipartite if and only if it admits a 2-click partition. And a 2-click partition is just when we can take all the vertices in a graph, split them up into 2 groups, and the subgraphs induced by those 2 groups must be all-to-all connected graphs, or clicks. And in this case, this is a co-bipartite graph, since we see that we can split the top 3 vertices up into 1 group, and that subgraph is all-to-all connected. And we can also split up the bottom 2 vertices into an all-to-all connected subgraph. Now, this allows us to restate our theorem as saying that a bidirected entanglement summoning task is achievable if and only if the causal graph admits a 2-click partition. Now, why is this characterization a bit more natural? Well, we recall that single state summoning requires a tournament, or an all-to-all connected graph. So really, we can interpret our theorem as telling us that a bidirected summoning task needs to admit a partitioning that can summon half of a bell pair through each of the clicks. So for example, here, all of these are achievable entanglement summoning tasks, because the way we can go about completing the task is really we can just do single state summoning of 1/2 of a bell pair through one all-to-all connected graph, and then summon the other half in the other click. So yeah, this was a pretty nice natural characterization that we got of our theorem in terms of the original causal graph. Yeah, any questions about the bidirected case?
Yeah, I had a slightly more general question. So here, just to make sure that I'm following the model, we are So in this communication diamond thingy that we had in the beginning, we are allowing quantum communication, I suppose, right? Because the shares that you were moving around are quantum shares, I suppose. Is that correct?
Sorry, could
Or is
you
it just, sorry.
repeat?
I was just asking about the communication model. So I think there were these causal diamonds, right? Or
Yeah.
whatever, I don't know what they were called. And
yeah,
the
the
point was
causal.
that you could communicate. Right, so that you could communicate, like is the intersection, right? So with this communication, is it classical or quantum?
Yeah, it's well, it can be
It's
either
quantum, right?
classical or quantum. Yeah.
Yeah, sure.
Yeah,
No, but in
whichever.
the sense that for your secret sharing scheme, I suppose you require, I guess the shares are quantum, right? So for
Yeah.
the protocol you described, you do need to be able to send quantum states.
Yeah, that's true.
Is that's okay? So do you think it's is it immediate? Whether if one restricts to completely classical communication, anything would change? Is it like immediately impossible, or because you're allowed to have a shared resource to begin with, right?
Yes. That's a great question. I haven't thought about.
I think you could just teleport, like, because we allow pre-shared and like some big pre-shared entangled state, you
So
could
you
add
just
some
teleport. Okay,
entangled states and teleport, and it would go through the same way.
Okay,
makes sense.
great. Okay. Any other questions? Okay. If not, I'll move on to the more general case. So far now, previous work by Alex and collaborators characterized the oriented entanglement summoning task, and what we just went over covered the bidirective case, but now we want to try and tackle the most general case where we can have a combination of both oriented and bidirected edges. What we'll do is we'll implement a similar protocol to the previous case where we map the problem of sharing or the problem of summoning to sharing, but now we have a bit of a caveat, and there's a big difference from the bidirected case where now we need to handle neighboring calls when there's an oriented edge. So we saw that in the bidirected case, if, for example, D1 and D3 received calls, then we didn't have to consider this case because we can just handle it with a dedicated EPR pair because they can see that their neighbor got a call. But we can't do that if, for example, D1 and D4 receive calls because D1 will have no way of knowing if D4 received a call. So we must consider this case separately. So this little discrepancy from the bidirected and general case will actually make it so that the protocol we implement will only give us a set of sufficient conditions, but their necessity is yet to be proven. So we will show that we have a large class of achievable entanglement summoning setups, but we're still not sure if the conditions we find are necessary. So with that being said, we'll implement the exact same protocol as before. We'll pre-share some resource, map that resource that goes to every single diamond into a bunch of different shares based on how many outgoing edges that diamond has. And if that diamond receives no call, it will forward all its shares. But if it receives a call, it will keep all its shares. So going through this example again, we'll pre-share some state that has now been split into 4 different shares, send it off to every single diamond, and once again, split it up into these new subsystems. Now, in the case where non-neighboring diamonds receive calls, this is handled exactly like the bidirected case. If, say, D1 and D2 get calls, all the other shares will all the other diamonds will simply forward their shares, and D1 and D2 will keep all their shares. And at the end of the day, the shares that end up at those 2 diamonds look like this, and the T's are defined exactly as before. T1 will be all the shares that D1 gets when it receives a call, and T2 will be the same. And we now have this authorized pair of T1 and T2 because they must be able to recover a bell pair using these shares. But now let's analyze what happens when we get a call between 2 diamonds that share an oriented edge. Now D1, since it got a call, it's not going to forward any shares, even though D4 also received a call. So D4 is going to expect to receive shares from all the diamonds that point into it, but it won't get one. It won't get one from D1. So what we'll find is that the authorized pair that is formed in this setup from the D4 diamond is going to be almost identical, except for the fact that it doesn't receive a share from D1. So this is how the information will be spread. It's almost exactly identical to the bidirected case, except this channel is not used. And so the authorized pair that results from this is we have T1, which is the exact same as before. It is just all the shares that D1 will get when it receives a call. But now we have this new notation, which we'll call T4 without 1, which is going to be the subsystems that D4 receives minus the shares from D1, since D1 received a call and didn't forward anything. So now we have these new authorized pairs that will be denoted by Ti and Tj without I. And that is also authorized since it must recover a Bell pair. Now, what will the access pair graph look like in this case? So the body of the graph will be the same as before. We saw that when non-neighboring diamonds receive calls, this is exactly like the bidirected case where we just take the undirected complement of our original causal graph. But now, these calls with the oriented edges sort of form a branch from the body of the graph. So when D1 and D4 get calls, we know that the authorized pair is going to be T1 and some set T4 without 1, which is just T4 without the share received from D1. Similarly, for D2 and D3, we also have this branch out, forming this authorization between T2 and T3 without 2. So the access pair graph that we get when we implement this protocol for the general case is again going to be the complement of the causal graph with these wings spanning from T1 if a diamond D1 has an outgoing edge in the causal graph. Now, since we have this access pair structure defined from the summoning task, all that's left to do is again determine when it satisfies monogamy, and we'll hence know that it is achievable. And what we find is that there are 4 different conditions that if the causal graph satisfies them all, then it is an achievable summoning task. So these are a sufficient set of conditions that we come up with. The first condition is the same condition that we saw in the bidirected case, that we can't have any odd cycles in the access pair graph. And what we find is that the odd cycles could ever only occur in the body of the graph, since the rest of the graph is just these wings that are only connected to one other vertex in the access pair graph. And so we just can't have any odd cycles in the undirected complement of the original causal graph. And so as an example, here's a graph that doesn't satisfy this. The pentagon bidirected case doesn't satisfy having no odd cycles in its complement. So yeah, this is when no odd cycles is not satisfied. Now, in terms of the original graph, this corresponds again to the fact that the causal graph must admit a 2-click partitioning, as we saw in the earlier section. Yeah. And then the next condition is called M1, which tells us that we cannot have an even length path between 2 diamonds with an oriented edge in the complement graph. So an example of a graph that doesn't satisfy this is this one. We see that there is an oriented edge between D1 to D4, but in the complement graph, we have this path of length 4, which means that this graph would not satisfy the M1 condition. Now, in terms of the original causal graph, the condition that we find is equivalent is that if we have some oriented edge between 2 diamonds, we have to have at least 1 2-click partitioning of that causal graph where those 2 diamonds belong to different clicks. So for example, in this graph, the only 2-click partitioning is these three vertices and these two vertices, but we see that D1 and D4 are always in the same two-click partition, so that M1 star is violated. The next condition is no two out. So if we have a diamond that points with an oriented edge to two different diamonds, then we must have a causal connection between those diamonds. And here's an example of a graph that violates this. So we see that D1 has an oriented edge to both D3 and D4, but they do not have a causal connection between them in the causal graph. So this graph violates the condition M2. And this is already a condition that is on the original causal graph, so we don't elaborate on this further. And then finally, the last condition is this condition M3, which is a bit more convoluted, but it states that if we have two pairs of diamonds, one that has an oriented edge to its partner and another with an oriented edge to its partner, and we have an even complement between those two diamonds in the complement, then the diamonds that they point into must have a causal connection. So just to illustrate this with a graph that doesn't satisfy this, we see here that D1 points into D4 and D5 points into D2. And we have that there's an even path in the complement graph between D1 and D5, but D2 and D4 do not have a causal connection between them. So M3 is violated. But if we put any sort of causal connection between D4 and D2, then it would be satisfied. Then in the causal graph, this condition is sort of similarly stated as M1, which tells us that we need to have, if it is the case that D1 in this example and D5 belong to the same click in every two-click partitioning of the causal graph, then we must have that the diamonds I pointed to are causally connected. But in this case, we see that is violated. So if in our paper, we show that if we have some entanglement summoning task that is mapped to a sharing scheme with the access paragraph that we saw results from the protocol, if it satisfies all of these conditions, then it is achievable. So let's look at an example of an achievable task. The task that we considered in our example is one such instance of an achievable general entanglement summoning task. So first, we see that there are no odd cycles in the complement graph, which is just going to be these two blue lines. As for M1, we see that there are only two oriented edges, which are D1 to D4 and D2 to D3, but there are no paths in the complement from D1 to D4 or D2 to D3, so M1 is automatically satisfied. As for M2, we don't have any diamonds that have more than one directed outgoing edge, so M2 is automatically satisfied as well. And then finally, as for M3, if we have some, the only two outgoing edges that we have here are D1 to D4 and then D2 to D3. And even though D4 and D3 are not causally connected, there's only an odd length path between D1 and D2. So this condition is satisfied as well. So this is an example of an achievable general entanglement summoning task. Now, as I mentioned, all of these conditions, we proved sufficiency, but we're still not sure if they're necessary yet. We know that the no odd cycles and M2 conditions are necessary, but M1 and M3 are left up for debate. And the reason for this is that in the bidirected case, it is very clear that when we map the summoning task to a sharing scheme, it is the most general way to complete the summoning task. But in the directed case, we made the choice that if a diamond with a directed outgoing edge receives a call, it will not forward any quantum information. But there might be a protocol where they would still want to forward some quantum information to their neighbors, in which case the protocol that we came up with would not be the most general way to complete the task. But the good news is, I guess, is that we haven't found any counterexample to our conditions, so we suspect that they're necessary, but we leave that to future work. And yeah, so that's all I had for today. So thanks for listening.